Hello, I welcome you all. The problem reads: a man kicks the 150 grams ball such that it leaves the ground at an angle of 60 degrees and it strikes the ground at the same elevation a distance of 12 meters away. Determine the impulse of his foot on the ball at A. Neglect the impulse caused by the ball's weight while it is being kicked. This problem is coming from the Engineering Mechanics and Dynamics 13th edition by R.C. Hibbeler. So in chapter 15, we are dealing with linear impulse. Okay, mind you, we are from the other chapters. The previous chapter, chapter 14, we are dealing with principle of work and energy and the conservation of energy, right? And then in the other chapter, chapter 13, we are just dealing with using the equations of motions and kinematic equations to solve problems. So all these other methods that we've dealt with can also be used to solve problems in this chapter 15. But in chapter 15, we are dealing with linear impulse and linear momentum. Okay. So what is this linear impulse and linear momentum? I'm going to be using these letters to designate them. So we are saying linear impulse is the applied force over a period of time. This is impulse. Okay, this is impulse. This is linear impulse. Okay, so this one is linear impulse. It is the applied force over a period of time. And what is linear momentum? This is the change in the velocity of an object that has mass, right? All right. So this is linear momentum. Okay. So how do the two relate? So linear momentum is just equal to linear impulse is equal to linear momentum. So the applied force over a period of time of force times the change in the time is equal to mass times the change in velocity. And this is a vector quantity. Okay, and by this we mean it has both direction and magnitude. Okay, so let's look at what is happening right now. We have a foot that kicks this ball. Okay, so we have the ball. If this point is 0, and then we have this point here which is 12 meters at 0 meter, and so the ball is kicked here, and we've been told that this ball covers a distance of 100 meters and then falls at the same elevation where it was kicked. Then at this point, the ball experiences some velocity. So let's look at what happens here. Okay, so here it has also velocity there. At the same elevation, it will have the same velocity. This is velocity, this is velocity. So let's talk about what happens at the point when the foot is in contact with the ball. At the point when the foot is in contact with the ball, and we are assuming this ball is at rest, okay, it's either it is stationary, it is motionless, or it is moving at constant motion, or constant motion. So let's assume it is at rest. Okay, so we can assume this. So we say assume S naught is just equal to 0. Okay, so it is at rest. So the moment the foot is in contact with the ball, this foot transmits, or it imparts or applies a force to the ball over a certain period of time, and this is what we are calling impulse. And this impulse that is imparted to this particular ball, changes the momentum of this ball. All right, it changes the momentum of this ball. So basically what we need to calculate is we want to find the impulse at A, which is equal to the mass times the change in velocity, right? So the change in velocity here, this change in velocity is just equal to V final minus V initial. But at A, we know that V initial is just going to be equal to 0, all right? And then V final is what we are looking for. This is what we need to calculate. So we are going to use kinematics from here to calculate this V final. So it will have components. We have one component there, we have another component there, right? 60 degrees. So we have Vx and then we have Vy. Vx will not experience any acceleration, but Vy will. So we are going to use the kinematic equations here. We have S equal to S naught plus V naught t plus half A C t squared. Remember this equation? So we are going to work out this in both axes. We'll have two equations, and then with two unknowns, then we'll solve the value of Vx and Vy and then find V, which is going to be our V final. And this is the one we are going to use here in this equation to calculate the impulse, right? Is that okay? Sure. So let's do so. Right. So let's using kinematics equations to solve for V. So we are saying V will have two components here. So we have this component like so, and then we have another component. Okay, like so. So let's call this here Vy, and then this one Vx. Okay, so we know that we can, assuming that of course this is going to undergo constant acceleration in the vertical direction, so we can use this derived equation. So say S is equal to S naught plus V naught t, okay, plus half ACT squared. So let's start with the horizontal motion. Along the horizontal motion, we have what do we have? So this one here is just equal to V cos 60. This one is V sine 60. So we have our V naught, which is just going to be equal to Vx and is equal to V cos 60. Our AC here is equal to 0, and our S naught is equal to 0. Sorry, our S naught, S is equal to 0, and then our S is equal to 12 meters. Okay, let's say 12. So with this information, we can simply say our 12 is just equal to V cos 60, okay, then times T. So this is one equation. This is equation 1. Then we go to the vertical motion, right? Go to the vertical motion. So what do we have? Vertical motion, we do have S is equal to 0. Final S is equal to 0. S naught is also equal to, this one is our reference, it's just equal to 0. And then our V naught is just equal to Vy, which is equal to V sine 16. And our AC is just equal to minus 9.81. Then later on, if we are to write this just becomes equal to, so it's 0 equals to V sine 16, okay, times T minus half by 9.81 times T squared. So we have two equations right now. So let's call this equation 2. So with these two equations, we can solve them simultaneously so that we get our solution. Okay. So the idea is to find the velocity v. So solving the two equations simultaneously, solving the two equations, we have so we have this one here. We'll say t here is just equal to 12. Can you replace the t there, right? I think so. 12 divided by b cos 16, and replacing it in the other equation, we'll have 0 equal to v sine 16, okay, by 12 divided by v cos 16, okay, minus half. So this one becomes 0.5 by 9.81 minus a 4.905, and then by 12 divided by v cos 16 squared, right? Right? Yes. So of course this becomes tan yes. So when we work out this just becomes 0 is equal to 12 tan 16, 12 tan 16 minus, in fact we can write it like this, 12 tan 16, this is equal to we multiply that by 12 squared, so this just becomes a 706.32 divided by v squared cos squared, like so. Okay, and therefore our v is just going to be equal to, cos 16 squared times 12 tan 16, okay, like so. And then we have 706.32 divided by that, and then square root of that. So we find that this becomes 11.66 meters per second. Let me get back again. So we have 4.905 by 12 squared, 706, 702, okay. So then we have cos 60 squared times 12 tan 60. Okay, then 706.32 divided by answer. All right, and then square root of that. All right, so once we have this, then let's now find the impulse. So we know that impulse is just equal to, our impulse is equal to the impulse, linear impulse. Okay, so linear impulse, okay, I, so this I is just equal to m change in velocity. Okay, and then we have our v naught here equal to 0, and we have our v final equal to 11.66. This is at A. Don't confuse this. This is at A. Okay, VA, this is all at A. Okay. All right. Therefore, our impulse at A is just equal to the mass mean total is 150 grams. So we can change this to kgs. Okay. 0.1, we divide it just by 1,000. And then we multiply this by the change in our velocity, which is just 11. So let me write this properly once more again. So this is equal to the mass times V final minus V naught, where m is equal to 0.15 kgs. And therefore, our I just becomes equal to, which is linear momentum at A. Our I at A is equal to, our I at A is going to be equal to m, which is just 0.15 times V final minus V naught. This is just equal to 11.66. So if we did the multiplication there, we get that's a 0.15 by 11.66. This is 1.749. Therefore, it just becomes 1.75. What are the units? So this is force time. So we can say Newton second, or it can also be kg meters per second, right? I think this is about it. We've calculated the impulse at A. Okay, we've calculated the impulse at A, and I hope this particular video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and sharing my channel. Bye bye, and see you in my next screencast.